Now let's derive the equation for transformer EMF. For that, if suppose this is the transformer core and these two represents the transformer limbs and these two represents the transformer yoke, and let this be the primary winding which to be wound on the limb of this transformer. But please keep in mind that there will be insulation present between the transformer winding and transformer core. Let the insulation be this one, on which the transformer primary winding and transformer secondary winding are wound like this, and this is the input supply given to the primary winding, and let us suppose the secondary winding is left open circuited, that is under no load. Therefore, as no load is connected, the primary current is called as no load current, and because of which here EMF E1 is induced, and let this flux in the core be phi1 and the EMF induced because of this flux in secondary winding be E2. So now the flux is of sinusoidal nature. Let this be the maximum flux phi m, and the time period be t, and if you observe here, flux phi changes from minimum to maximum in t by 4 seconds, that is equal to 1 by 4 fh. Therefore, average rate of change of flux is equal to maximum flux phi m by 1 by 4f, where maximum flux phi m is equal to flux density into cross section of the core. Therefore, that is equal to phi m into 4f, that is equal to 4 phi m into f Webers. Therefore, as this is the average rate of change of flux, in order to get the RMS value, we need to multiply this average value with form factor. Therefore, RMS value of EMF per turn is equal to 1.11 into 4 phi m into f, that is equal to 4.44 phi m into f. Therefore, as this is the EMF per turn, then the EMF induced in primary winding, which is consisting of N1 turns, implies E1 is equal to N1 into 4.44 phi m into f, that is equal to 4.44 N1 into phi m into f. Similarly, E2 is equal to 4.44 phi m into N2 into f. If you observe these two equations, phi m is same because core flux is same in transformer core, and if you divide E2 by E1, which will give you N2 by N1. This is represented with K, where K is called transformation ratio constant. This is the one of the important relation, but the thing you must note from this EMF equation is not this. That is, EMF is directly proportional to the phi into f, which implies flux phi is directly proportional to E by f. As induced EMF is directly proportional to input voltage, you can take phi is directly proportional to V by f. This is the important relation which you must note from the EMF equation of transformer. Why means, if frequency decreases, flux will increase. If flux will increase, then there is a chance of magnetic saturation of the core. If the magnetic saturation happens, transformer will drag more magnetizing current from the input. If more magnetizing current, then power factor will decrease. How it will decrease means, now let's analyze that. Let us consider ideal transformer. In this case, if you observe, primary winding is of inductive nature, therefore no load, primary current and flux will be in exactly 90 degrees lagging with input voltage. And this is the case if we assume permeability is constant. But with excitation, permeability will change. Therefore, in case of normal transformer, V and flux will be like this and I naught will be like this. Therefore, I naught will have two components, one along the flux, which is called magnetizing component of no load current, and the other current which is drawn along the input voltage is called IC, which is core loss component of no load current, and let the initial power factor angle be phi naught. Now let us suppose frequency is decreased. If frequency decreased, flux will increase. If flux will increase, transformer will drive more magnetizing current. So if this is the initial magnetizing current, now let us suppose the magnetizing current is increased to this value. Therefore, now the resultant will be like this. And if you observe now, phi naught angle is increased. If phi naught is increased, power factor will decrease. Therefore, we must protect the transformer from getting into saturation. For that, the solution is, if there is decrease in frequency, we need to maintain V by F ratio constant. If we can maintain V by F ratio constant, phi will be constant. Therefore, transformer core will not enter into saturation. So, to make V by F constant with change in frequency, we need to change the input voltage. Therefore, if there is decrease in frequency, we must increase voltage. By that, we can make the V by F ratio constant, and by that we can make the flux constant, so that we can save the transformer from entering into saturation. And initial power factor angle will be around 60 degrees to 70 degrees. That implies initial power factor will be around 0.2. This is what you must note from the EMF equation of transformer. Thank you for watching, and if you like this video and my presentation, please like this video, share this video, and do subscribe to my channel. Thank you. See you in next lecture.